Okay, so we're going to continue with where we left off in lecture. And remember, our goal is we're trying to estimate P over Z, the integral of P over Z e to the IZ over this upper, the semicircle in the upper half plane. Okay, so we said we're going to split S sub R into two regions. So we've got A, which is from here to here. And then we've got B, which is from here to here and from here to here. All right. So let's get to it. So we're going to, so we're just using the triangle inequality. Clearly the integral over all of SR is going to be the integral over A plus the integral over B. And then I just used my triangle inequality to get this. So let's see here. So the, so let's see here. So the integral over A, let's do that. P of Z over Q of Z e to the IZ dz. Now keep in mind that the problem that we had from before, was as these points, as our point Z, so for Z in SR, as Z is approaching the x-axis, we lose our bound on e to the I Z, right? The best we can do is say it's less than or equal to 1, and we need to make a sharper estimate, right? So we are doing that by cutting off our domain, and let's go ahead and see what we have here. So this is going to be less than or equal to the length of A times the supremum for all Z and A of P of Z over Q of Z e to the IZ. Okay? Oh, you can't see that really. Okay, there we go. All right. Now the length of A is going to be less than or equal to, so let me see here, maybe on the side here. The length of A is going to be less than or equal to pi r, because pi r is the length of SR, right? So that's the length of the entire semicircle. We're not using the entire semicircle, we're using less of that. So we can still do an upper bound of pi r. And for here, we will have a constant, some constant, over the modulus of Z, because remember, we are requiring that the degree of P be strictly less than the degree of Q, right? So what we're doing is we are taking this P of Z over Q of Z and estimating it as some constant over the modulus of Z. This is the big idea, right? Now, the sup of this e to the IZ is going to be times the sup e to the IZ, the modulus of e to the IZ, and this is Z and A. But remember, we said that the sup of e to the IZ, that's going to be the sup of, so let's see here, maybe I can go off to the side here. Okay, so remember, if we have e to the IZ, what's the modulus of it? E to the I, x plus IY, right? Which is going to give us e to the minus y plus ix, okay? And then we'll just get e to the minus y, right? Now, if Z is in A, then Z equals x plus IY implies that y is bigger than or equal to h, right? Which implies minus y is less than or equal to minus h. So e to the minus y is going to be less than e to the minus h. So from these computations, the sup of Z and A of e to the IZ is going to be less than or equal to e to the minus h. Make sense? So this is what we're going to use for our sup of e to the iz, the modulus of e to the iz. So we'll get here pi times r times, now look at this, if z, so if z is in A, that means that the modulus of z has to be r, right? And now we've got over here e to the minus h. Okay. Let me erase this. So if we multiply this all together, the constant times pi is another constant. The r's cancel out, so we've got a constant times, just write constant. We've got a constant times e to the minus h. Okay, so that's our estimate for this first part right here. Now let's do an estimate for the second inequality, the integral over b. Okay, so the integral over b, p of z over q of z dz. Sorry, just kidding. It should be e to the iz dz. Is going to be less than or equal to, no surprise here, the length of b times the supremum of p of z over q of z, e to the iz, and this is for all z in b. Now here, we're going to estimate the length of b. We can estimate it with, let's see here. So remember, we've got two of these little pieces here, right? So if I zoom in and let me try to do a different color. So if I do, I'm going to use red. So I want to estimate this length right here, and then I'll multiply it by 2, right? So zooming in, this is the circumference of this circle, right? So imagine, so if we blow it up, from here to here is h, right? And I want this arc right here. Do you see what's going on? So this is h, and then I want this length right here. And we can easily estimate that the length of this arc is going to be less than 2 times h, right? So if this is h, then going from here to here can't be more than twice h, because that's basically a little bit bigger than a triangle, right? And even if this is h, even if this were h, which is not, you'll still have 2h as the hypotenuse. But that's not even going to be h, that's going to be really small. So what do we have? 2h here, 2h here. We're going to use 4h as our estimate. That's a reasonable estimate for the length of b. So we'll have 4h. And for this supremum, we will have, let's see here, so we'll have again a constant over r for the supremum of p over q, the modulus of p over q. And for this e to the iz, we'll do exactly with the same reason that we had before. The best we can do is estimate it as 1, right? Because this point here, r comma 0 is always going to be in there, which is going to have your y value equal to 0, right? So the modulus of e to the iz, right? So if z is in b, implies that z could be just r, right? Which is r plus I0, right? Now this is, we computed, this is e to the minus y, so that would be e to the minus 0.
It's 22 hours.
Thank you. So the sup over all e to the iz, the modulus of e to the iz is going to be 1 for that little piece here. So the best we can do is to say a constant times h over r. Now, remember our goal, our ultimate goal, was to show that this, we wanted to show that this goes to 0 as r goes to plus infinity, right? So currently we have that the integral over SR is less than or equal to the modulus of the integral over A plus the modulus of the integral over B, right? And we said that this is going to be less than or equal to a constant times e to the negative h and the second sum is going to be a constant times h over r. So if we choose h to make this go to 0 as r goes to plus infinity. So choose h so that constant over e to the h plus constant times h over r goes to 0 as r goes to infinity. What works? Well, how about h equal to square root of r? That'll work, right? So if h is equal to square root of r, then this is going to 0. So we get that our integral goes to 0. Does that make sense? Okay, so let's see this in practice. We're gonna work on a specific example, and our specific example is going to be, let's compute the integral from negative infinity to infinity, sine x over x. Okay. So the first thing I want to note is that this is, so if we put this in our format, we've got, this is like p of x over q of x sine x, right? So p is going to be 1. Q of x is going to be x, right? The problem, though, is that notice that we're going to have to take into account that q can be 0, in particular at the origin. Now, we know that just looking here, sine x over x, the limit as x goes to 0 of sine x over x is 1. So we do not have a pole here. We have a removable singularity. So it'll be okay for us to integrate, right? So we have a removable singularity, at the origin, since limit as x goes to 0 sine x over x is equal to 1, right? But we do have to take this into account when we're doing our contour. So we're going to do a slight modification. Instead of doing something where we're doing our little semicircle and cutting it off at IH, I don't know if you can see that. You probably can. Instead of doing this, here's what we need to do. We're going to do this. Does that make sense? Okay, so this means our gamma sub r, b, okay, so we're going to go, so let me try to blow this up. So what's happening is, let me use a different color. Okay, so this is epsilon, this is r, this is negative epsilon, this is negative r, and we've got our semicircle. So our contour, let me see if I can just do it like this. Our contour starts here, goes around the semicircle, goes this way, and then goes around the little semicircle. Okay, so we're going to let gamma sub r be the interval from epsilon to r, and then that semicircle, and then the interval from negative r to negative epsilon, and lastly negative s epsilon. Because notice that for s epsilon, which is the small semicircle, we will need to have a clockwise orientation, so we need to use negative s epsilon, right? Gets that little clockwise orientation on the semicircle in the upper half plane with the radius epsilon. Okay, so what do we need to do here? Let's see. All right. So the question is, so remember, we are going to integrate. So this is the goal. So the game plan. Integrate. We're going to integrate 1 over z, e to the I z, over gamma sub r. That's the game plan. And we're going to let epsilon go to 0 and let r go to infinity, right? Notice that as we integrate over these intervals, 1 over z, e to the I z, dz, what do we get? We're just going to get epsilon to r, 1 over t, e to the it, dt, right? What is this going to be? This is going to be integral from epsilon to r, cosine t, plus I sine t. Yes, over t, dt, right? So we're going to have integral epsilon to r, cosine t over t, dt, plus I times the integral epsilon to r, sine t over t, dt, right? So we'll have that, but we'll also have that the integral going from negative r to negative epsilon of 1 over z, e to the iz dz, is going to be integral from negative r to negative epsilon. And we'll have the same thing, cosine t over t dt, plus I integral negative r, negative epsilon, sine t over t dt, right? Here's the kicker. So if I'm going to integrate from negative r to negative epsilon, plus integrating from epsilon to r, I'm going to get the integral from epsilon to r, cosine t over t dt, plus the integral from negative r to negative epsilon, cosine t over t dt, right? Plus the integral plus I times the integral from epsilon to r of sine t over t dt, plus integral negative r, negative epsilon, sine t over t dt, right? Here's the deal. The deal is this is going to equal 0 because they're going to cancel each other out, right? So cosine t over t is going to be odd. Cosine t over t is an odd function, right? So, and then this sine t over t is even. So this part down here is going to be equal to 2 times the integral from epsilon to r sine t over t dt. So what do we have? So let's see here. So the integral over gamma sub r of 1 over z e to the I z dz is equal to the integral. Now if we're going from epsilon to r plus the integral from negative r to negative epsilon plus the integral over SR minus the integral S epsilon, right? These are equal to 2I times the integral from epsilon to r of, so what is that going to be? Cosine sine t over t dt, right? And then we've got this, so we'll have plus the integral of e to the iz over z dz over sr, and then minus the integral e to the iz over z dz s epsilon. All of that is equal to this integral over gamma sub r, our big contour, e to the iz over z dz. But now, it is also the case that, so we can use the residue theorem, we can also use Cauchy's theorem to say what is this integral here is going to be equal to 0. Why? Because remember, z equals 0 is a removable, well no, because of the way we cut our contour, we omitted, we actually don't even have to worry about is z removable, is z not removable. We don't have to worry about it because our contour, 0 is not in the interior of our contour. So our function here that we're integrating is holomorphic e to the iz over z, holomorphic over, right, in a neighborhood containing this, right? So all we have to do, we can always just avoid, right? We can avoid the origin. We're good to go. So this integral is just going to be 0. So this is good for us because this means that 2I times the integral from epsilon to r sine t over t dt is equal to the integral s epsilon e to the iz over z dz minus the integral over sr e to the iz over z dz. Okay. So let's see, what do we have here? So let's compute. Let's work on this integral here. So the integral here, s epsilon e to the iz over z dz, is, what's going on here? Well, we've got an issue. So here's what we're going to do to navigate this. Now, the origin is not a removable singularity here, right? But notice, if we rewrite this as, so let's rewrite the integral s epsilon e to the iz minus 1 over z dz, right? Now we can say that this is going to be less than or equal to the length of s epsilon times the supremum of e to the iz.
It's 20 to 15.
Minus 1 over z And this is z in s epsilon. Now, what is the length of s epsilon? That's just going to be pi times epsilon. Okay, and now over here, we've got the sup of this e to the iz minus 1 over z, z in s epsilon. Now, why are we looking at e to the iz minus 1 over z? That's the question. The answer is because now z equals 0 is a removable singularity, right? So now how do we notice that? Because look, okay, what's the limit as z goes to 0? E to the iz over z. The bottom's going to be going to 0, right? The top, the numerator, is going to be going to 1. Put in e to the iz minus 1, and we're good to go, right? So this, now we would use L'Hopital's rule. We'd take the derivative, and we would get limit z goes to 0, and that'd be I e to the iz over 1. So we would just get, as z goes to 0, we just get I, right? So 0 is a removable singularity, which of e to the iz minus 1 over z, which means that this sup here exists. It's some kind of constant, right? So e to the iz minus 1 over z is bounded near the origin. So we're guaranteed to have this be some constant. So let's say constant, some constant, since the mapping z sent to e to the iz minus 1 over z has a removable singularity at z equals 0, so it is bounded on a neighborhood near the origin, right? So what does that mean for us? That tells us that, so the integral s epsilon e to the iz minus 1 over z dz goes to 0. Why? As epsilon goes to 0, because it's less than a constant times epsilon, right? So constant, epsilon, let epsilon go to 0, this magnitude is going to 0, so the complex numbers inside of there must be headed towards the origin as well. Okay, what does that mean for us? Well, we can compute integral s epsilon e to the iz over z dz. It's going to go to the integral over s epsilon of 1 over z dz as epsilon goes to 0. And did you see how I did that? What did I do? I said the integral s epsilon e to the iz minus 1 over z dz is equal to the integral s epsilon e to the iz over z dz minus the integral 1 over z dz s epsilon. This I can compute. This is going to equal integral. Now s epsilon, remember, is the semicircle. So we're going to go from 0 to pi. And what's my parameterization going to be? So for s epsilon, I'm going to go from 0 to pi. That's going to be my domain. Codomain is going to be complex numbers. Theta is going to be sent to epsilon e to the I theta. Yes? So this will be 1 over epsilon e to the I theta. What is my derivative? I epsilon e to the I theta. So I have d theta. What do we have here? So my epsilon e to the I theta cancels out. The I, bring it out. So I have I. Integral 0 to pi of just 1 d theta. That's just pi I, right? So my integral over s epsilon e to the I theta, e to the I z minus 1 over z dz. So this, right, goes to 0. But this is equal to the integral s epsilon e to the iz over z dz minus pi I. So this goes to 0, right? And this is all as epsilon goes to 0. So integral s epsilon e to the iz over z dz goes to pi I. Does that make sense? Okay. And this is as epsilon goes to 0. Okay, so we know that our s epsilon, this right here, this is going to, maybe I should use green here. This is going to pi I. So now we need to figure out what's going on with the SR, the integral over SR. So let's do that. So our integral over SR and this is e to the I z over z dz. Well, this is exactly what we did before. So we show that this, right, remember we can take SR and split it up into the part here is A, and then here is B, right? So this is going to be equal to the integral over A plus the integral over B, right? And so the modulus over A of e to the iz over z dz is going to be less than or equal to the length of A times the sup of e to the iz over z. And this is z belonging to A, right? But now if z belongs to A, so the length of A, we're going to estimate that by just pi r. If z belongs to A, then that denominator is just going to be r, right? Sup z and A, right? So the r's cancel out, so we just have pi times the sup of the modulus of e to the iz, z and A. We're going to let A, we're going to, remember this is IH, but for us it turned out that a good thing to choose was let H be the square root of R. Yeah? So this is going to be e to the, we said this is going to be e to the minus square root of R pi, right? So this integral e to the iz over z dz goes to 0 as r goes to infinity. So notice that A depends on r, right? So that's why we're saying as r goes to infinity, this integral is going to 0. And we do the same or a similar estimate for B. Integral over B, e to the iz over z dz is going to go to 0 as r goes to infinity, right? So we did the computations. We did the computations in the beginning of this video. See early computations in video. Okay. And so what does this mean? This tells us that, here we are, this goes to 0. Okay, as r goes to infinity. Make sense? So let's just write this. Let me try to copy. Okay. And paste. Okay. So let's just recap here. So the limit as r goes to infinity and as epsilon goes to 0 of the integral s epsilon e to the iz over z dz minus the integral sr e to the iz over z dz is going to equal pi I, right? But now this is the same as 2I times the integral epsilon r sine t over t dt, right? Limit r goes to infinity and epsilon goes to 0 is going to be pi I, right? So what is this? This is the integral from 0 to infinity sine t over t dt is going to be pi over 2. There we go. Right? And now again, so if you want to go from negative infinity to infinity, sine t over t dt, that's just going to be pi. It'll be twice going from 0 to infinity. Okay? And that's it. So notice that we started off with our contour, which is our usual closed semicircle, and we modified it to take into account the fact that we had a pole or a singularity at the origin, right? And so you can imagine that you might be in a situation where you're cutting out several little holes, right, at each of your poles. Z1, Z2, Z3, and Z4, right? And then you're doing slight modifications to this overall semicircle shape. Okay, so we talked about this a little bit, but on Thursday, the next contour, I think we're going to do keyhole, which is, so this is epsilon, right? So now look at this. If the diameter from here to here is epsilon, and the radius from here to here is r, right? You're letting r go to infinity, you're letting epsilon go to 0. In the limit, you've got the plane with the positive x-axis removed, right? And there's nothing special about going in this direction. You could also do the same type of analysis like that, right? And you could get so imagine if you're trying to integrate something with log, you'd probably want to integrate over a contour like this, okay? And then the last one, we'll see if we have time. I think I'm actually going to start with this one, is the sector. So instead of having your theta go from 0 to pi, you're going to have your theta go from 0 to some fixed alpha, right? So this is a subsection of the example that we did today.